I'll also hold a review session tomorrow at 2:30 right here in this room. Oh, that's nice.
Thank you.
Let's see how this works today. Okay, let's pick up where we left off at. We want to get back into alkene reactions today, hopefully. But let's finish up with alkynes. We'll go back to alkenes and we'll look at some that we left for you to do. And we'll incorporate more stereochemistry. We need to also do thermodynamics. Those calculations, I reckon we'll do those tomorrow. There's a video I'd like to show, one of those reactions at the top of that thermodynamics page. Okay? Please be ready to discuss and finish up the thermodynamics tomorrow. Alkyne reactions. Okay, we left off with Tautomerization. Is that right? Where we're at? Is that what I said? Alkynes, yes. Question?
Do you have extra alkyne? I don't have to. You need them back in lab.
You didn't have one on yesterday?
I thought it was in the email, so I went back and I think it was.
Okay. We can hydrate the alkyne once. It makes an enol, and the enol is not stable. Most enols aren't stable. Most enols will tautomerize to the carbonyl form. That is, the pi bond will end up between the carbon and the oxygen. This also involves relocation of a single hydrogen. That hydrogen is relocated here, right? It's definition of tautomers. Mechanism for the tautomers. Okay, we're still in the same flask. We still have H3O plus. Okay. Alkene. First step is the alkene reacts with the H plus. Have we ever done that? Sure, we've been doing that for several days now. Where are we going to leave cation, left or right? Correct, on the left. So it swings out this way, and we get new H on the end. What's here? Carbocation, because it no longer has 4 bonds, right? Anything new there? Should be nothing new there. Look where we have a new H, out here, where we need a new H. Okay? Now, what can we do here? We did this yesterday, I believe. I think it was yesterday. We had a chlorine here. And remember the chloro, and we did something here? These electrons move here. What was that process called? It's just a process we're doing on the board.
Resonance.
Yes, we can do resonance. Because on day 1, if we needed a bond here, we would have said, hey, we want to use this lone pair and share and make a bond. We would have did that on day 1. Boom, 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 boom. New H there. Now we have double bond to oxygen. H there. We haven't lost it. Okay. Let's make sure this is very precise. These electrons, right? And on the quiz, you need to work on the mechanisms, majority of you. A few very good. We had perfect 10, 8s and 9s, etc. A few that are just some minor details and good. But then a few, or more than a few, that's like you've never seen an arrow being used before. We've been using arrows on the board for several days now. It's the language of organic chemistry. It's the expectation of what you should know. You'll be tested on your use of arrows on the test. Doesn't bode well at this point. If I can help you, let me know. Office hours at 11 to 12, third floor. I think the office is listed on the syllabus. Love to see some of you. Bring your questions with you. Okay, these electrons move in, make pi bond, one lone pair left. Lo and behold, that's a positive charge. That's resonance. Resonance arrow. Whenever you do resonance, the true structure is really neither of these. It's a blend between the two. That is, it's not just a plain cation. There's some bonding here that's illustrated by this structure. Okay? But look how much closer the resonance structure gets us to home. What do we need to do to get home? Get rid of the H. And we're home. That's it. That's your mechanism. What do you want to use to get rid of the H? Well, there had to be a minus here. Okay, we did generically. Or we could use what?
Water.
Or you could use water. And say it with me. These electrons.
Electrons.
I mean, we don't just do something like that. What does that arrow mean? By the way, if you got a WDAM, that stands for what does arrow mean? It means, I don't know what your arrow means. Because it's what is this? H and 2 electrons are shooting off into space? No, that's not correct. Or you may get a WDAM when you use an arrow correct. You use an arrow correctly, but then what you show is didn't come from that arrow movement. So I say, what does this arrow mean? Because it don't mean this. So that's another way you might have got a WDAM. Water, these electrons can bond to H. These electrons can move on to oxygen to become the second lone pair. That's final product. And we reform H3O+. We started with H+, we end up with H+. Of course, H+ don't exist by itself. It's bonded to water here or something. So the H+ was the catalyst, right? Tautomerization is catalyzed by H+. It can also be catalyzed by hydroxide. There's your mechanism for that rearrangement. It actually should not be any new steps. We've seen alkenes react. The resonance we've done a couple of times, yeah. It's very important whenever you can draw resonance structures. And then we take the proton off. So we put a proton on. Okay, there's a mnemonic that, you ever heard of oil rig? Oxidation is lost. Those are called mnemonics. Roy G. Biv for your electromagnetic spectrum, yeah? Okay. There's one for the tautomerization process. It's called Oreo, like the cookie. Okay? I have no idea who made this one up. All right? Oreo. It stands for what you're doing here with each step. We put a proton on. H+ on. Correct? Didn't we put a proton on? That's the first O, on. Then what did we do on the board? We did some resonance. R-E, resonance. What did we do at the end? Here's our main thing. What did we do? We took a proton off. Yes. This is your tautomerization mechanism right here. Oreo. Anytime you do a tautomerization, Oreo is your mechanism. Anytime. Now, if you're under basic conditions, this is acidic condition. Under basic conditions, the O's reverse on the end. Because under basic conditions, the first thing you would do is take a proton off. Then you would do resonance. Then you would put it back on. Okay? But we're under acidic conditions. When you're under acidic conditions, you put protons on. going to be the first thing. Now, you got to be careful. This is only 2 steps. It's a 2-step mechanism. Because as we learn more about resonance, resonance is really not a step. Resonance is just something we do on the board. That is, once the proton is added, this is the cation. It's only one thing. But that one thing is hard to show because it's a blend. It's like colors. This is pink. But if pink's hard to show for some reason, maybe I talk about red and white. And I say red and white, and the true structure is somewhere in between. What's in between red and white? Yeah, can you visualize what pink would look like? I can only show red and white because the pink is a little vague. That's what's going on here. It's only one thing. So you put proton on and you take it off. Resonance is something we just do on the board, on our paper. Resonance doesn't happen in the flask. Okay? Oreo, questions about the tautomerization mechanism? When you're asked to show a mechanism, the answer is not tautomerization. Okay? I just say that because I had a couple of students before say, what's the mechanism? Show the mechanism, and the answer will be right then. It's not the mechanism. What is the mechanism for the tautomerization? Boards are nice to clean. Somebody clean it. Do something to it. A good way to remember Oreo, not found in any textbook. Recognizing tautomers. Which of the following are enol tautomers, or enol forms, or enol tautomers, of the compounds shown in the box? What'd you get for this one? First two? Now, this question is sort of a little loaded, but it's the first two. Because the second two ain't even enols. It's asking you enol. Those are not even enols, right? Because the OH is not on the ene. So if you look at it that way, then yeah. But, now these are enols, but are they enols of that? What's the definition of an enol?
This has resonance.
What?
It must have resonance.
It must have resonance?
Well, it has.
No, the mechanism going between the two involves resonance. No.
Just an alcohol.
Relocation of a single hydrogen and at least
one.
is that what's going on if you go from there? Yeah. Pi bond has been relocated, and if you look at it, one H has been moved from there. There's two. Now how many here? Only one. That one H has been moved here. There you go. Yeah, the first two are both enol tautomers of the compound in the box. How about down here? Are the following tautomers? A little more complex, but the definition doesn't change. Are these tautomers? Who got yes? Who got no?
Yes, they are.
Yes.
Saying yes.
Good, yes, they are top 10.
It's not the original.
Because only one atom has been relocated. What? One of these H's is now where?
Right there, yeah.
Right there. Has anything else moved?
Behind on.
Okay, well, is any other atoms moved? No. But we have pi bonds that have moved. How many pi bonds? 2. That's at least one. Yeah, we said at least one. We didn't say only one. It could be 6. Those are tautomers. Could you show a mechanism in going between the two?
Sure.
Under acidic conditions, what would you do first? So you would take proton off. Under acidic conditions, you typically put protons on. Then you would do resonance. Then you would take it off. So you put it on here, do resonance, and you would take it off of there. Yeah, that's the same thing. You can do it. Although that type of resonance we haven't quite seen yet. We've only seen resonance with a lone pair. Once you move into organic, well, we'll cover resonance, believe it or not. We haven't covered it yet. We're just next week. Those are tautomers. Okay, can we use our reagents like hydroboration oxidation with alkynes? Yes, we can. What are we doing here? Looks like we're hydrating. That's a hydration method. Okay, it's convoluted a little bit. It's more than just water, but ultimately that's what it leads to. It leads to hydration of the pi bond. Okay. What's going on? Pi bond attacks what?
The BH3.
The boron, which is electrophilic because it has no octet, right? Where are we going to leave cation?
Left.
Correct. So maybe we should draw that out on our scratch paper. 1, 2, 3, 4, 5. Many of you started with 6 carbons on the quiz and then drew a structure with 7 carbons. Please keep track of your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. On the end now is the boron. That's a minus charge. Pi bond here. Okay, we had 2 pi bonds. One of them attacked boron. What do we do? Leave a plus here? Yeah? Mechanistic thinking. We don't just have to pull a product out of the air. What happens next?
Boron's going to throw a proton.
Yeah, this is not actually formed because this guy throws an H into 2 electrons here. Yeah? You got an H there and a BH2 here. And the BH2 is now neutral. But the boron and the H are cis on this double bond, right? Because if the boron is this way, the H has to be that way because it comes from the boron. It can't be bonded over here if it came from the boron. And since there's no free rotation here, we can just say, yeah, they're going to be fixed cis. There you go. That's in step 1. That's your hydroboration. It only does it once. It only does it once. We can maybe argue why, or I've never really thought about it much, but that's in step 1. What does the magic step do?
The OH plays in.
Places that with OH, magically delicious. And that is what I have in the brackets, right? There you go. There's your enol. Get rid of that H, it's there. Yep. So that's not a lot new. But that's an enol. And enols are typically not stable. They undergo rearrangement to the carbonyl form. I kind of wish I hadn't shown that and just asked you to draw it. What's a tautomer going to look like? Carbonyl tautomer. Well, it's going to be that, yeah? Which is, in this case, is an aldehyde. I like to draw in the H of my aldehydes. The H on the end carbon, it's there. Tautomer, this becomes double bond, and ultimately this H moves here. Now, mechanistically, it doesn't just do that. That's not a mechanism. So we don't want to, we've got to be careful about illustrating something with arrows. But ultimately, that becomes pi bond, and this H is removed from there. Pi bond there instead of here, and you get an extra H here. Well, that's that. I have just not drawn this H in. Go back to the enol. How many H's here?
1,
1. The second carbon has 1, but here the second carbon has
2.
2. See, there's a new H there. This H is relocated to here. Now, there's an H here. I just drew it in there. Like I said, I like to draw in the H's of my aldehydes. Most people typically do. They look a little odd without them.
So we should do the mechanism or you not doing that?
Well, there's two types of questions. Predict the product. Predict the product doesn't require a mechanism. That doesn't mean you shouldn't be doing it on my scrap paper, because the mechanism, it's like in math. You know, what's 68 times 93? Well, I'll maybe just ask you to give me the answer. That doesn't mean you don't use your scratch paper and do your formula and come up with the answer. That's how you get your answer. So the instructor may say, just get it, or show your work. To show your work is more like show the mechanism. And usually when you're asked a mechanism question, you're given the problem. Where the other would be you supply the product. Okay. So it undergoes tautomerization. In this case, it's aldehyde. Happens to be an aldehyde. These are in equilibrium, okay? This is an equilibrium set of arrows, and this is favored. That's why that's longer. Those are not resonance structures. If you look at resonance structures, when you do resonance, you never move any atoms. Only electrons. If you move atoms, you're not doing resonance. So this is an outcome using our hydroboration method. It hydrates once and then it undergoes tautomerization. This tautomerization would be catalyzed by base, because when it happens, you're under basic conditions.
Can you do the tautomerization?
With base?
For this one?
Okay, let's do it
It
with...
seems to be working differently than the last one.
Okay. Well, I don't know why it's different. What's different about it?
Because you said the H from the OH will come onto.
Essentially, this H ends up here.
Okay.
So,
I must just be doing it.
That's the same thing over here. Essentially, this H ends up here. Right? It was the same thing over there. It's now gone. There's now an extra H here. It's the same as before. But again, like I said, this is under basic conditions. We can do the mechanism under basic conditions. Oreo. Under basic conditions, O stands for what? The first O. Off. Because bases take protons off. Which proton do you want to take off?
for the alcohol?
The one that needs to be taken off. Which one needs to be taken off?
Off of the alcohol.
The one on the oxygen, because it ain't there anymore. That's the one. All right, let's draw this bond in, please. Okay. When you do mechanisms, you need more descript, okay? Here, this doing this is not sufficient. It's not sufficient. You either need to show this ionized and attack an H+, or you need to show something covalent. And when it's covalent, you attack the H and you kick these off. Just moving an arrow towards the reagent is not sufficient. So there needs to be some precision there. Okay, let's draw this bond in. You can do this, but it's usually not big enough. We have hydroxide. That's our catalyst. These electrons take the H. It's just an acid-base reaction. That leads to that plus water. You need to show that we're going here with just a reaction. That's just a progression error. Go to this intermediate. This is an equilibrium. This may not even be the favored form at equilibrium. We could assess using pKa's. That may be the favored form. That doesn't mean we can't get a little bit of this. Okay, that's a different discussion. All right, now what do we do after we take proton off? Resonance. O, read O. Off, resonance, on. Now the resonance here we've never done before. We'll start doing it next week. The resonance here is where we're going to take these electrons and move them in here. But this carbon can only make 4 bonds. So we're going to move these electrons out. This is what I'm going to call the old in and out movement of electrons. Now we're only moving pi electrons. That means we're showing a resonance structure. Boom, 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 boom. Now, you may not have been able to show these arrows, but once I showed them, what do they mean? You should know that. What does this arrow mean to you? Yes, this is moving in to make pi bond. So now we have pi bond between oxygen. 2 lone pairs left because one of them moved in to make pi bond. What does this mean? The 2 electrons in the pi bond are moving out onto carbon to become what? No. Talking about electrons. The electrons become what? A lone pair. It's the opposite of this. We had moved the lone pair in to make pi bond. It's pushing them back onto the carbon. Okay? Well, that's it. But we have charge. That's now neutral, but the carbon is now minus.
So it's the opposite of the catalyst.
Yeah, that's opposite of the Do you see? We're pushing the electrons back onto the carbon as opposed to, for example, here we could move these in and we get pi bond back. But there we moved them out onto carbon. That's what that means. Okay? This is resonance. All we did is move pi electrons. Whenever you do resonance, the true structure is actually in between. We now got red and white, and I'm trying to tell you that the true structure is pink.
So this is how we get the space for the hydrogen to come back in.
This is how we're going to get there, yes. Because now we did resonance. Off, what did we do? Off. We took proton off. We did resonance. Now what do you want to do? On. Where do you want to put proton on? Well, right here, because it needs an extra H. There's one there. There's one there. There's one H here, but we need 2. So we want to put one on there. What's going to supply the H?
The water.
Water. This takes an H from water. These electrons move back onto oxygen. What does that give? If these electrons make bond to H, and these electrons move on to oxygen, it gives that plus what? What? It gives that, right? And what did we call this at the beginning?
Catalyst.
Catalyst. Catalyst reformed. There you go. Off, resonance on here. Oreo. So we did a little introducing and a little new resonance. Mainly because we were asked to show this mechanism. We'll do more of that type of resonance. Our resonance structure is nothing more than, it's the same positioning of all atoms. You're just showing the electrons in different places. All the atoms are in the same place. But over here I'm showing the electrons as a pi bond here, where over here I'm showing those electrons as an extra lone pair on oxygen. Okay? That's what resonance is. You can say which do you like better. We'll talk more about that next week. It's the old red, white, really it's pink. Okay, really it's a resonance hybrid. There you go. There's your basic base catalyzed tautomerization. Oreo. These are in equilibrium. Why is this favored? I don't know that we said that. Why is the carbonyl form favored? There's a Bill Gates is rich because he has more money answer. What's that answer? Why is it favored? Because it's more stable. That's why it's favored. But then I'll have to ask you, why is it more stable?
Because of resonance.
There's no resonance here. What resonance are you talking about?
Yeah.
That's kind of what it means by being more stable. What's more stable bonds about it? Here's a take home. Your C double bond O carbonyl typically is a very strong bonding arrangement. This is driven by forming the carbonyl. Okay? You can pull out tables and look at actual data. But that's kind of the statement we'll make. Carbonyl is a very strong bonding arrangement. It's driven towards that. Every step we showed in our mechanism is reversible. That's a true equilibrium. The more stable one's favored. It's stable, the carbonyl sort of is the driving factor. Okay. Reduction of alkynes. Just like we reduced alkenes with hydrogen, we can also do that with alkynes. But we do have two pi bonds. You take an alkyne, an internal alkyne, hydrogen gas, precious metal catalyst. What's your favorite precious metal catalyst? Platinum? Okay. Platinum. Palladium is probably the most common. Platinum works, not quite as well. The most active tends to be the R ones, ruthenium, rhodium. Those are pretty darn good. Palladium is most common. These here, group 10, nickel, palladium, platinum. Those are important. Those are most common. Rhodium tends to be a little bit more active. We can add two hydrogens. How? Metal surface, two darts, same side. Okay, so if we bring in two H's to the pi bonds, what do we get? We're going to get the alkene with two new H's. Now the two H's are on the same side because they came in from the metal surface, right? So it would look like this, and that's cis because the two main groups are cis. So hydrogenation of an alkyne gives a cis alkene. Should make sense, you know? But guess what? That's an alkene. Can alkenes react with hydrogen? Yeah, it can do it again, twice the fun. And when you add two more H's, well now each carbon has two H's, and it becomes just the alkane. So this would be sort of a double hydrogenation all the way down to the alkane. And we've totally reduced it. We've totally saturated it, right? 2 degrees of unsaturation. Now it's totally saturated with hydrogens by hydrogenation. Typically here you cannot isolate the alkene, so we put it in brackets. It's not isolated, but the reaction continues on.
Is that what the brackets mean for the?
Brackets means that it's not isolated. It's sort of, we're showing it on the board because it's informative to know that it's there. It's formed in the flask, but you can't really isolate it. It just reacts on.
It never stops.
It doesn't stop. It's very hard to isolate. Typically, because the second reaction is faster than the first reaction, as soon as some forms, it just continues on. We could get into maybe why. Not exactly sure that the second step is faster, but sometimes that's the case. Question?
So the first two that go on, they're cis to each other, or they're just on the same thing? So they're both coming at you, I guess, or away from you? Or the second two do the same thing?
Yeah, but look at this product. Is there any stereochemistry here? Yes, that's tetrahedral. One H is forward, one H is back. It doesn't matter. Look at this product. Here we go. Let's go back to stereochemistry. How many stereoisomers are possible for that compound? None. That is, if you say two, then draw them both. I mean, whatever you draw is going to be the same thing. Unless you don't have 4 carbons attached linearly. You can sit down and try it. And since no matter how you draw it, it's the same thing, then here's how you draw it. That's why it's usually just going to be drawn generically. That doesn't mean it's not tetrahedral. Yes, one H is forward, one H is back. Here it matters because here it can be cis or trans, but we know here you only get what? Only cis because those H's came in from the same side. Cis only. But there, it doesn't matter. It would really only matter if it stopped here. Or if you just asked to show the intermediate, and the intermediate would have to show cis, because we know mechanism. Okay, can it stop here? Often in organic chemistry, when we say it continues on, we're probably going to then show you a reaction where it can stop here. Well, that's down below. If you use a poison catalyst, what is that? If you use a poison catalyst with your hydrogen, it will stop at the alkene. Okay? You can get it to stop here typically in good yields to make it a useful reaction. What's a poison catalyst? First off, one of the most common is just called Lindlar's catalyst. If you ever see Lindlar's, that's an example of a poison catalyst. Usually a poison catalyst is where you take one of these precious metals and you add something to it to make it less active. You poison it. You partially ruin it. You make it less active. And in practice it works out. It's just a slower reaction, and we're not going to go into every single detail here, but it works out. And typically, it just doesn't continue on, so we X that out. It stops here. I'm not going to give you any other details other than it's poison, so it stops. Examples of poison. A lot of times you add heavy metals. Like you can take palladium and add barium carbonate, and the barium will kind of coordinate with the palladium and it'll partially ruin it, kind of poison it. And actually, Lindlar's catalyst is probably one of these. Sometimes you also add an amine, quinoline or something. These are examples. Lead or barium serve as poisons. Lindlar's is one that's very commonly is a name that's stated. Yeah? And it would be a cis. So this is a way to make cis alkenes from alkynes. Questions on that page? What about transalkenes? Can you convert an alkyne to a transalkene? You can. Not with hydrogen gas though. With hydrogen gas, the H's always come in from the same side. Here, we got a product where the H's are on opposite sides. That's not going to come from hydrogenation. How can you do that? It's a brand new type of reaction here. You can do that using sodium and ammonia. What's the charge of the sodium here?
Plus.
No.
No? Minus?
No. What? If it was plus or minus, I should have showed plus or minus. It's neutral. This is sodium metal. You can put a 0 above it. That often means the oxidation state is 0. Sodium metal. And you do this in liquid ammonia. Ammonia is a gas at room temperature. But if you cool it down to minus 33 or lower, the ammonia will condense to a liquid. And you can actually use liquid ammonia as a solvent. It's odd and unique, but it can be done. And that's done here. Okay? Terminology. Now this is a partial reduction, right? When you use a poison catalyst, that was also a partial reduction, but we're not fully reducing. Okay? So this is partial reduction to the trans product. And this is going to be a radical reaction. This will be our first look at a radical reaction. This is also known as a dissolving metal reduction. First off, is this a reduction? How do you know it's a reduction?
It's going from the alkynes to alkene.
How do you know that's a reduction?
We added a hydrogen.
Because we're adding hydrogens. In organic chemistry, when you add hydrogens, that's typically a reduction. Let me ask you this trick question. If you remove hydrogens, that's a
Opposite of reduction.
the opposite of reduction. It's a oxidation. Okay? So if you add H's in organic chemistry, it's typically reduction. In organic chemistry, we evaluate redox a little bit differently than Gen Chem. Now you can make the two mesh together if you discuss them, but adding H's, removing H's. Adding H's is a reduction. We've added two H's here. It's a reduction. Dissolving metal, because the metal, the sodium metal is going to dissolve. That's very, very simple. Very simple generic terminology or description of the reaction. You'll see a number of dissolving metal reductions along the way, including organic too. Okay, first thing, when you add sodium to ammonia, you generate what's called solvated electrons. Sodium and ammonia, it leads to sodium plus. Plus what? Plus an electron. Oh, there's right? If this gives up an electron. The only way to get this is to lose an electron. Okay? Now the electron is solvated with ammonia. Okay? analogous to hydrogen bonding or some type of IMF. What does a single electron look like? Well, that's what we're dealing with. Sometimes this is called a SET. You know the SAT? This is an SET, like elephant. Single electron transfer. This is an amazing reaction. Why does this happen? First off, if you add sodium to ammonia, it will turn blue. Real brilliant blue. You can probably find the video online. The electrons are being generated and solvated, and somehow it produces color. I'm not sure I can explain. We get electrons. It's an amazing process. Mother Nature's amazing chemistry here. You can dive into this and try to fully understand it as far as we'll go. We create electrons. Okay, electron, we can show it maybe as a dot. That's just like a single electron instead of a long pair of electrons. The electron adds into the pi bond. Usually we've always been, the pi bond's been nucleophilic and reacting with something. Here the electron comes in. And when we move a single electron, we don't use a full arrow, we use a half arrow, a fishhook arrow. That's for moving 2 electrons. This is for moving 1. 1 electron comes in here. These 2 move over here. By the way, when we're done, we need to show the fully balanced reaction with all byproducts here. Let's be able to show that. Okay, comes in. What does this lead to? One electron here, it pumped in. Now what does this arrow mean? What is now here?
A lone pair?
A lone pair. Charge. What's charge to?
Carbon?
Is this
No.
charged? No. Is this charged?
Yes.
Yes, it's a minus. Okay, how many electrons does this carbon own? 1 in each bond, so it owns 1, 2, 3. Plus that one, that's 4. How many is it supposed to own? 4. It's not tricky. Not tricky. Determining charge is not tricky. And if you do it over here, this one owns 5. Okay. There you go. Of course, if you add an electron to a neutral compound, if you add a minus to a neutral, your species should be minus. Okay? There you go. This is a radical. A radical is something with an unpaired electron. We've never seen a radical in this course before, I don't think. I've never showed you one. Everything has had pair, like a lone pair or a bonding pair. It's a radical. Okay. This is a carbanion. This is strongly basic. Does this look like a good base? What's a good base?
Anions.
Anions?
Yes.
Well, there you go, it's an anion. But so is this. Which one's a stronger base? Which one is mad being minus? Carbon, yeah. More electronegative, it's okay being minus. We see chloride all the time. It's a strong base, it don't want to be minus. This one's a proton. What can supply a proton? Yes. Ammonia actually acts as an acid. Have you ever seen ammonia act as an acid?
No.
Ammonia's typically a base. Ammonia acts as an acid, and these electrons take an H, leave this behind, and what does this give? By the way, we never addressed an important issue here. That gives, I'll draw in the H, okay? There's the H that's there. Plus what? NH2, and what's its charge? Minus. That's 2 lone pairs, right? As shown by this arrow. Question. I showed this trans and nobody asked why. Because the important thing here is underlined. It's trans. Why did I show trans? Why didn't I show this cis? Well, here's the answer. Because here it had a choice. It had a choice, and the system chose trans because trans is more stable. Right? That's the reason. When we do a hydrogenation, and the H's come in, does it have a choice of being cis or trans, or does it have to be cis? It has to be, because the H's come in, and it can't be trans. Here it had a choice. Okay? It had a choice. Is somebody willing to stand up and let me illustrate something? Somebody stand up. One person stand up. Thank you. Okay? You can just stay right there. Okay? All right? Just stand there. Okay? Let me ask you, why do you have your hands down like this? Why didn't you have them up like this?
So smart.
Yeah. You had a choice, and you chose to put your hands down. Why? It's more stable. It's a lower energy. That's what happened here. It chose trans because it's better. Thank you. That make sense? You didn't stand up like, you don't walk around like this. You choose to walk with your hands down because that's better, right? That's it. If you want a more scientific explanation, I mean, that's it. It chose, it had a choice. That's why you get trans here. Okay, from here. Next, you actually need another electron. Another electron pumps in here, and what do you get? What do you get then? Boom. There's new H here. Now what do we have here? 2. That's a lone pair. What's the charge now?
Negative.
Negative. Boom, we get that. Last step. How do we get home? We need another ammonia. These electrons take the H, these stay behind, and we get final product. There's an H on each carbon. Here you go. Okay, fully balanced. If we show this, what do we get? We got that plus what? We got Na plus. How many of those did we generate? Well, we needed 2 electrons. 1 electron here and 1 electron there. So how many sodiums did we need? Each sodium gives you 1. 2. And 2 of those. What else did we make on the board?
NH2.
Yes, right? There's the first one. I didn't show the second one, but that gives that plus NH2 minus. We make 2 of those. Plus 2 NH2 minuses. Now, it's not balanced, because that tells us we need 2 sodiums and 2 ammoniums. Now everything should be balanced. 2 sodiums on this side, 2 sodiums on that side. But the sodium is now ion. And guess what? The ion will be dissolved. But when you first put the sodium in, it's not dissolved. But as the reaction proceeds, it dissolves. These ions will dissolve in the very polar solvent. This is almost like water. Ions will be soluble in ammonia. Okay? Now, how can I show this instead of like that? I could show this 2NaNH2. Right? Because if I said we form sodium plus chloride, 2 of each, what's another way to show this? I could just say we form 2 sodium chlorides. Right? you may often just see it shown like that. And when you see this, yeah, that's plus, that's minus. 2 of each. So that's what we formed here, dissolving metal reduction. Questions about this? Yes?
So for the 2 electrons, the sodium plus, I'm trying to count out the 2 sodium pluses. You just don't write them, you just write the electron negative that you add to the first one on the alkyne.
This electron came from that process, basically doing twice.
Okay, and that's why you add it later. Up there.
Yeah, we needed 2 electrons, so this had to take place twice. So you had 2 sodiums, you created that, you created 2 electrons. I used them both in my mechanism. I used the first one here, and I used the second one here. We need a 2 here, that's why we put a 2 there. If we want to balance it. That's the second time I balanced a reaction. Hopefully I won't do it again. Radical reaction. Using a fish-hook arrow. It's called a single electron process. Or single electron transfer, SET. Questions? So that's how you can make a transalkene from a alkyne.
What are the applications for this? Like, why do they go through all the trouble just to make transalkenes from alkynes?
Why would they? Who's they?
Like, why would chemists,
Okay.
I'm just curious as to.
Well, what if you had a transalkene? We can show you the examples of some. How you want to make it?
Huh?
How would you make it?
I mean, look, yeah, I guess I'm just curious.
This is a way to make transalkenes.
The applications today.
Well, I try to show you a lot of drugs. I mean, I could find you a transalkene, tell you how important it is, and then I could say, do you know how to make transalkenes? One way would be, yeah, I can make it from an alkyne. Then maybe you would say, well, how do I make the alkyne? Well, you're into multi-step synthesis. We're developing a toolbox of reactions, and synthesis is a huge part of organic chemistry. But here's another thing. Half of this is showing the transformation of an alkyne to a transalkene. The other half is something that sometimes you guys don't realize. The other half is you practicing your understanding of reaction mechanisms. And every time we do one, we reinforce over and over and over. And so then by the end of organic, you're like, okay, I think I finally understand what a mechanism is about. Because we practiced, we did so many. So this is also a vehicle for just learning general concepts of mechanisms and reactivity. And the sidelights, like, why does sodium give up an electron? Well, in Gen Chem, we're taught that sodium wants to become like argon by losing an electron or something up there. No, argon, right? No.
Nope.
Yeah, the previous ones. Yeah, I've had Gen Chem a long time. Okay. Well, how does it do that? Well, one way is to put in ammonia, and it does it. Then you can say, well, why does it do it? Well, at that point, I'm telling you, we can't just keep going on and on. It's fascinating. And so you get experience with chemistry and the fascination of it. If you want more, you have to go get more. But then, if you can do this, well, what if I give you another radical reaction? Can you understand it easier and quicker after we went through this? Good questions. Keep asking. We'll do more. On day one, I told you at the end of Organic 2, you'll be amazed at how much you learned. Yes, the details, but more importantly, the global just understanding of organic chemistry that will hopefully last with you for years and years, that you don't just forget when the course is over. Because if you do, then the course has been worthless. Okay. Acidity of terminal alkynes. We sort of mentioned this earlier with the acid base. A terminal alkyne, the hydrogen here, has a pK of about 25. That's the most acidic you'll see for a plain hydrocarbon. Plain hydrocarbon. All right? We'll talk about bases. Why? Here's the resulting, where we're going. What type of stability does this anion have that allows us to do this? What's the stability of it that you can discuss? I'm telling you this has some stability. Why?
A lot of S characters, so close to the nucleus.
Again?
Electrons are held close to the nucleus, a lot of S character.
A lot of S character. Yeah, that carbanion is sp. It's 50% S. The electrons are held tight to the nucleus. That's the explanation of why it has some stability now, okay? It's a hybridization effect. Look back at the acid-base handout. We covered hybridization effects. We covered this exact deal here, okay? Now, pK of 25 is not that acidic. I mean, carboxylic acid is 5, alcohols are 16. Not that acidic, but I'm telling you it's the most acidic of hydrocarbons. It's acidic that you can do chemistry, and you can do this reasonably. Type of bases, N-butyllithium. What is N-butyllithium? N stands for normal or straight chain. So we have a butyl. It's a butyl anion, and a lithium sits with it. That's N-butyllithium. It's an alkane anion. This is one of the strongest bases you can have. These electrons will take this H, leave those behind. We get that plus what? When that takes an H, butane. Boop, boop, boop. Now has an H. Well, this has a pKa of greater than 40. It's even less acidic. Okay, you got 25 and 40. Which is favored? Which side's favored? 40, the weaker base. So that side's favored by how much? That's 100 gazillion. Question, is this strong enough to deprotonate the terminal alkyne and come this way? Yeah, 100 gazillion is, yeah. And lithium is a type of base that you might use. You can also use this, which looks familiar. That's the sodium NH2 that we formed above. By the way, that's called sodium amide. Amide. What's an amide? That sounds like a functional group with a carbonyl. Well, an amide is also a nitrogen anion. What do you call a chlorine? What's a chlorine anion called? Chloride. Amine. Amide. You see, it's unfortunately the same name. So it's sort of, okay. Sodium amide. That's often shortened to sodamide. Okay? Sodamide is a common base used to deprotonate terminal alkynes. In textbooks, in my handout. In practice, it's a lousy base because it won't dissolve. The textbooks love it. Okay? You've got NH2 minus. These electrons take the H, leave that behind. We get this. The sodium sits with that, plus ammonium. Ammonia as an acid has a pK of 35. Which side's favored?
The right side?
the right side by 10 billion. That's pretty favorable.
Didn't we just make that?
Yeah.
Yes, this was formed in the reaction above.
Yeah.
Yes. Now, this is not sodium metal. This is sodium plus and minus. That's a salt. Okay? Importantly, you cannot use hydroxide to deprotonate this. Because if you did, hydroxide takes H, we get this plus water. Well, this is 25, and water is 16, right? Which side's favored here?
Left side.
See, the starting material side. Thus, we say that hydroxide is not strong enough to deprotonate a terminal alkyne. You need stronger bases. What stronger bases are available when they're, okay? Again, that was a terrible base. Indolithium is the one I would recommend. It's more soluble because it's got carbons. By the way, you don't want to do these in water because it'll take the proton from water. Okay? Actually, here, the reverse reaction is favored, right? Isn't the reverse favored here? That is, if you have an anion, a terminal alkyne anion, and water,
It's gonna take it.
that'll take an H from water and go this way. That's the result of, well, that's the understanding of this down here. Miners' helmets from the 1800s. They'd have a helmet and they'd have a flame up here. Because they didn't have flashlights and batteries, 200 years ago. But they'd have a flame on their head. And they'd wear it and then they could see. That would give light. Burning up there. You gotta watch out for your hairspray and stuff. Okay? What was it? They had calcium carbide. What is calcium carbide? CaC2. Lewis structure. Well, if you do the Lewis structure, it's going to be this. And then the calcium 2 plus goes with those 2 minuses. What is this? That's a double anion of what we're dealing with here. Calcium carbide. It's a mineral. You can find this in nature. It's maybe not. It may be easily produced, though. It's been produced for hundreds of years. But the anion will react with water, just like the reverse here, right? And when it does, with both of them, you get this. That is, you'll end up with H's on the end. C2H2 plus calcium hydroxide. But what is this? That's acetylene. Now, it's a common name. What would be the IUPAC name? 2 carbons, ethyne. Nobody calls it ethyne. It goes by acetylene, which you probably heard. What's acetylene used for? Torches. Okay. What they do here is they have a chamber. You can find on eBay. You can find some of these old ones or diagrams of it. It's a chamber where the carbide sits, and then they have water in some chamber, and the water drips onto the carbide. And when it drips onto the carbide, this reaction takes place in the gas. And then they have a line and the gas comes out, but you can light it and it will burn. They can set up the engineering. And it will give a continuous stream of acetylene and a continuous flame. And that's how they had old miners' helmets or old lamps that ran off of carbide.
Seriously, very
Well, you could have that. I'm sure that happened, but the alternative is going to the cave with no light, and so you had to do something. Okay, so that's the reverse of that. I think it's pretty cool. Yeah. Yeah. Let's take a 2-minute break.
First I was afraid, I was
At UCLA Chemistry, they make videos about organic chemistry. There's a variety on YouTube. You can find them. That's one of the best ones I've seen. Some of the others are almost hard to listen to. I thought that one was pretty darn good. You saw a couple of things in there. Tautomerize. Okay, there's also some terms that we'll see in the next week. SN2, E1. Grignard. Grignard's covered in organic 2 here mainly. UCLA, I Will Survive. You can find it online. They have like competitions. They make videos. Have a little fun. Document camera.
Do that.
Okay, that's the chemistry of alkynes. Very similar reactions to alkenes. We have a little bit new, tautomerization, yeah. That mechanism, tautomers. We have the radical reaction to get transalkenes. And the acidity of terminal alkynes is very important. Making the carbanion, sometimes called the acetylide anion. Understanding the reverse, and the reverse application, you know, carbide, it's reverse application where the anion is reacting with water, going the other way. Make acetylene gas. Questions about alkynes? And then something down below, how do you make alkynes? We'll look at the synthesis of alkynes during test 3, covered later. Okay, we can actually synthesize alkynes. We'll do that later. Here we just used them. If you think about it, we're also just using alkenes. We haven't synthesized an alkene, I don't think. Test 3, we'll actually learn how to make alkenes. Now, a lot of textbooks actually reverse test 2 and test 3 the way I do it. And actually, I don't follow Klein. Klein covers, I think, alkenes, my test 3 material first. I think it's better to cover reactions of alkenes first before we do that other chemistry. But I'm unique. Most others cover the other chemistry first. Okay, couple of miscellaneous things here. Hydration of acetylene, that was a big moment back in the late 1800s. You can look at the mechanism. It should make sense. You can read about the history of that. You ask, why do we want to do that? Well, why would you want to hydrate acetylene? Well, read about it. It led to industry growing and here's just a drug with an alkyne up there, but it's of course got lots of other components to it. Used to treat type 2 diabetes. Got an alkyne. Also got a chirocarbon. Is an RS. Who says R? Who says S? All right. Some reactions over here.
R.
Handwritten reactions. SN2 is a test 3 reaction. EAS and Frito Crafts were covered in organic 2. There's an alkyne reaction. Well, we can point out this right here. What's the first step here? Into lithium. They have this structure here. What's the most acidic hydrogen in this compound? Because NBL lithium is a very strong base. Most acidic hydrogen.
Guess it's going to be the
Yes. Oh, they're all, H's are all on carbon. We talked about this, yeah, that H. The n-butyl lithium makes the anion here, the acid-base mechanism. Anion, yeah. Then these electrons are going to react with zinc. Now, these transition metals have some covalent character. You could maybe show it partially ionic. And if these react with the zinc, carbon-zinc bond, it's kind of how this bond is made. You first make the anion, then it becomes a reactive nucleophile to react with the zinc. Okay. From there, they then do what's called a Negishi reaction with the alkyne zinc. This is advanced chemistry of an alkyne. This won Nobel Prize in 2010. But ultimately, they're putting together this alkyne linkage here between these two rings using some chemistry. On the very back is an example of another synthesis, and this one includes a well, let's look at it. They're making compound 1. Compound 1 has this 2-carbon saturated chain here. It's a saturated sort of ethyl linkage. They actually form this molecule by forming this linkage here. How do they do it?
Precious metal.
This is some advanced chemistry. Wittig is actually covered in Organic 2. That's test 3 for us. That's an advanced reaction. But essentially, they're combining these by alkyne chemistry, and they're making the alkyne so we can do that chemistry. Then what do they do to the alkyne? This is something we should know and just covered. They reduce it with hydrogen. Palladium on carbon. Now, carbon is not a poison. Often you disperse the palladium on charcoal. It just makes the greater surface area. Basically, it's just palladium. This is going to convert the alkyne to what? The alkane. First to the alkene, but doesn't stop with. That doesn't stop unless you use a poison catalyst. So it goes all the way to the alkane, and that's what they wanted. So they utilized alkyne chemistry, and they knew they could then reduce it to get that saturated ethyl group. So that's an example of one of the reactions we covered. Again, whenever I handwrite things in, it's either we're going to see it later, or maybe I'll refer to it. That's an organic, a Nobel Prize winning reaction. Okay, at this point we can sort of turn to the home stretch, see where we left off, where we need to go back and look at. I think let's go to the stereochemistry warm-up page. We covered all new material. We can start doing some questions. And in particular, go back and look at alkene reactions and look at the stereochemistry in even more detail. Let's see how we did on some of these. Zocor. There's Zocor, right? How many chiral carbons?
7.
7? Anybody get something different? Who said 7? Yep. Okay, let's count. 1, 2, 3, 4, 5, 6, 7. Are those the 7? Any other chiral carbons? Anybody see any others? I think that's it, 7. Good. Okay, how many possible stereoisomers for this drug?
128. 2 to 7.
2 to 9.
Why 2 to the 9? We got 7.
Oh, no, those are in rings, never mind.
Why'd you say 9 then?
Because I was thinking about those two, but they're in rings, so they can't be.
Can these become, that is, can this become, right now it is E. E. Could it become Z? No. Not a pi bond in a 6-member ring cannot be stereogenic. You cannot turn, skip the other. Yeah, those 2 alkenes are not stereogenic. The only stereogenic sites are the 7 chiral carbons. 2 to the 7 is 128. Okay? Did you draw all 128? Technically you could. If I gave you $1 million, could you be able to draw 128?
Yes.
Okay, thank you. Question?
How are you so easily able to determine which ones are chiral and not?
Chiral carbon is a tetrahedral carbon with 4 different things attached. That situation, the carbon will not have a plane of symmetry. That's a chiral carbon. Okay. How about that guy? Showing a Fisher projection with filament top and nothing at bottom. Let's see. I don't want to do too many up top. Any questions up top? I want to move down. Questions up top? How'd we do on those?
I had trouble like visualizing how to put it, the phenyl, or yeah, on the bottom.
With phenyl at top and ethyl at bottom.
Or,
Okay.
so
Phenyl at top, ethyl at bottom. So if the ethyl's at the bottom, where's the ground there?
I don't.
Right there.
Okay.
Over here, with ethyl near the ground, bottom. Okay. I can see why there might be a little trouble because it's a little bit different from the view that we did. Here's one thing I'll just remind you: keep your feet on the ground. Because a lot of times students will say, "I'm doing it like this," and I'll say, "Hold on now, your feet are in the air." Identify the ground. Think about that. We'll come back. We may do those at some point. Any other questions about those?
Can you post the answers, please?
I'll see if I have the answers to these. But I may want to just do these in class for a review session. I'll see if I have the answers. Let's look down here because this is, I wouldn't expect you to just do these. Some of these, yes, but I need to sort of show you a few things about these. Identify each of the following as chiral, achiral, or meso. Achiral, of course, meaning not chiral, non-chiral. First one.
Chiral.
What's the answer there?
It's chiral.
Chiral? Is it,
Yeah.
somebody say chiral?
I said chiral.
Achiral?
No.
How are you determining this? Okay,
No,
question. How do you
it's-
determine if something's chiral?
No, it wouldn't be.
Symmetry? What about symmetry? Doesn't have symmetry? Okay. So, everybody knows how to determine if something's chiral, right? Right. So, is this chiral? Who says chiral?
I don't think so.
3 people. Who says achiral? I'm not voting. I wonder what's going on. Yes, it's chiral. Because it has no plane of symmetry. It's chiral. Okay, next one. Chiral, achiral. Where's Waldo? That's what we're doing. Where's Waldo here?
Okay, so achiral.
Guys need to get in the game,
Or
or it's going to pass you by. Get in the game.
What about
Chiral,
meso?
achiral. Why? Plane of symmetry. There's Waldo. And if you have to plane of symmetry in the mirror image, it's going to be the same thing, meaning it's not chiral.
Could be meso.
So what do we want to put here? Meso? Why meso? Yeah, but water has a plane of symmetry, and water's not meso.
But they're mirror images.
It has two chiral carbons. And a compound that has chiral carbons, yet as a whole it's not chiral, is called meso. Right? Those carbons are chiral.
So
It's an example of a compound that has chiral carbons, yet as a whole it's not chiral.
So what's the difference between achiral and meso?
There is a difference. Both of these are achiral, but meso is more specific. Meso has chiral carbons, but it's not chiral. Water would be called achiral. Methane, achiral.
If there's no chiral carbon at all.
Meso is a special type of achiral. Is meso, because it does have chiral carbons. By the way, is the top one R or S? Bromine, carbon with bromine, carbon, R.
Yeah.
Bottom one, real quick, is what?
S.
How do you know it's S?
It's the mirror.
So it's a mirror. It should be S. If it ain't, then it ain't a mirror. Question.
I'm kind of confused about how we were stacking them before, like,
Okay.
on the first one at least. Why can you not stack those? Or if you can, I would think that you could stack them if you did it upside down.
Okay, if this looked in the mirror, it would see. If you look in the mirror, see that? Really, the question is the mirror image the same or different? These are different. If we had a model, you can see they would not stack. Look at this. Here's the two bromines. One's forward and one's back. Okay. Now, to make it over there, the bromines are on that side. Okay. One forward, one back. Now, if I turn around, the top bromine is forward, yet there it's back. If you try to stack them, you're going to have one bromine one way, one the other. But how do you know this? You could do that, you could do the model and do, but how do you know it? You could look for Waldo. Do you see a plane of symmetry? Is that a plane of symmetry? No. Is that a plane of symmetry?
No.
Well, clearly no, because there's not two bromines over here. So if you can't find a plane of symmetry, it tells you that the mirror image is going to be different.
So they don't stack them.
The next one
An antimer. And if something where the mirror image is different and it has an antimer, we call the whole compound chiral.
is it's meso.
Now we can call the whole compound chiral, or we can call individual carbons chiral. Each carbon is chiral. Each carbon is chiral. Yet the compound as a whole is not here. Answer here. You see Waldo?
No.
No plane of symmetry. If that was a bromine, yeah, but it's not. So those are not mirroring. So this is, since I can't find a plane of symmetry, that means the mirror image is going to be different. So this is chiral. It has two chiral carbons, and the whole thing is chiral. Okay, what about these over here? You want to do what? I thought you said, shouldn't we draw the fissure? And I was going to say, yes, we should, because the fissure is much easier to see planes of symmetry. That's one of the powers of the fissure projection. Or you could, once you know what you're doing, you could, there's some tricks, but for you, I recommend fissure projection. Okay? Draw this in a fissure and then answer the question. Let's see. Okay, we need to discuss this because what do you want to put in the top and bottom? Why chlorine? Because they're in the plane, and we said those are easier to put at top and bottom. Yes. So let's make this 1 at 4, and let's put chlorine 1 at the top. You could do the other if you want. Since 4 is at the bottom, this is going to be the ground. The 2 chiral carbons are going to be vertical compared to the ground. Let me stand here. With the top chlorine going away, what side's the methyl one? It's going behind the wall. So if I'm over here and it's going behind the wall, it's on my correct. So the chlorine going away, which that's what that means, the methyl is over here on the right. There's an undrilled hydrogen here. Hold on. Here. It's over here. It got to be. Because it's coming towards you, which is on my left. Okay? Let's look at the next carbon. With the chlorine going away, this methyl is on. Well, I need to come over here. Because it's only going away if I'm standing over here. The chlorine going away, the methyl's on the
Right.
correct. Chlorine going away, the methyl's on the right. H is here. Okay, now I'm going to eventually show you how to rotate these. Do I need to rotate that, or can I see the answer right there? What do you see? Plane of symmetry. Easier to see here, yeah? So what's the answer? Meso, because it does have chiral carbons. Yeah? Next one. Do that one. Somebody have an answer? I think this one we're going to have to rotate. I'll show you how to rotate. You say meso? Okay. Let's do it here. One chlorine is in the plane, the other one is not. Well, that's okay. We can put methyl at top. Methyl at top, chlorine at bottom. Things in the plane are easier to put at top and bottom, right? So the methyl at top, going away, that's what that means. With the methyl going away, let's see, methyl at top, chlorine at bottom, so the ground is here. On the ground, yeah. Methyl going away, the chlorine is on the left. Correct? And the electron H is on the right, because it's going. Now let's come down here. With chlorine going away, do I need to move over here? No. You see, it's not going straight away. It's coming a little bit down. Well, that one's not going straight away either. It's going a little bit up. That's okay. Looking down through here, with chlorine going away from me, so I'm up here hovering. Feet on the ground. The ground is here. Hovering up here. With chlorine going away, the methyl is on my correct. Chlorine going away, the methyl is on the left. The undrone H is here. There it is in a fissure. Now, certainly that's not a plane of symmetry because methyl needs to be here. Well, this has free rotation. It can rotate. Okay? I mean, if you got 2 back, let's make chlorine blue. Okay. Down here, chlorine's back, methyl's over here. Methyl's back, chlorine's over here. So there it is on the board. Well, let's put methyl here so we can see if the methyl's in mirror. So look, this can just turn like a clock. And if you want the methyl to be going back, how's the chlorine going to be? It's going to be going that way, right? You just turn this like this. You either like this or like that. I can turn this here. It's just turning. If the methyl comes here, the chlorine's going to go here, just like a clock dial. And the H will swing over there. That's what. And so if we do that, we get to, we can just do this and say, chlorine's now here, H moved over here, I just turned that, didn't do anything here, okay, I just rotated it, same compound. Now we can maybe look again. Methyls are mirroring. Is this a mirror image? I mean, is that mirroring? Well, methyls are, but no. I need chlorine here. Well, you could say, I could rotate this. If I move chlorine here, well, guess what? Then the methyl will go there. And that ain't going to mirror. It will never mirror.
Yeah. I looked at the top part wrong. What I did is I just stood my person in front of the top part instead of on the side of it, like you do on the board, instead of rotating the whole Fisher projection. I just imagine just looking.
You can tell me again if you need help there. You'll never find the plane of symmetry, and so if you can't find Waldo, what's the answer? Yeah, that's a chiral molecule.
So this is,
The mirror image of that would be different.
so we could have just used your shortcut here, right? The R.
You could have done what? Yeah, there are shortcuts. The more you.
Because they're both R, we would have
Are they
known.
both R?
They are, I think. So, no?
They better be the same, because if one was R and one was S, that would be a mirror plane. Because they are the same chlorine. Yeah. They better be the same. Are they both R?
They're both
chlorine?
R.
Yeah.
So then we
Yeah.
know.
So you know that that's not a mirror plane. There's no way you're going to get it to be a mirror plane, because one would have to be R, one would have to be S. So, yeah, that is a shortcut. It's chiral. It's RR. The mirror image would be SS, and those would be enantiomers of each other. The RS compound, which I believe is this, it's probably RS here. Its mirror image is the same exact thing. Okay, over here, how about the last one? Well, I'll let you do that one on your own because we're pushing time. Let's do a couple here to get you going on these, and please look at these overnight. We'll meet in lab right here at 2:30. 8:30 in the morning, and then 2:30 tomorrow afternoon if you'd like to have a review. Okay, these down here. We're still playing the same game. Where's Waldo? Playing symmetry here?
No.
Yes, plane of symmetry right through here.
Oh.
This side is mirroring this side. Half a chlorine mirroring half a chlorine coming forward. Half a bromine going back, mirroring half a bromine going back. It's a plane of symmetry.
So you can split.
You can split atoms.
Okay.
Just like you can split a piece of bread. Take a piece of bread, and you go right down and have two identical pieces that are just thin.
So just like planar carbon
Yeah.
stuff can't.
So, what do you want to call this compound?
Maybe so.
Isn't that even?
No, it's not even chiral. It's achiral.
These carbons are not even chiral.
It's big.
This compound has no chiral carbons. It has no enantiochemistry. It does have diastereochemistry. But these are trans. They can also be cis. That's diastereomeric relationship. This is achiral. What about that one?
No.
Hopefully this one's easy. Any plane of symmetry here? Obviously that's not a plane of symmetry, right? Obviously that's not a plane of symmetry. There's no plane of symmetry here. We have 3 chiral carbons here. No, it's no plane of symmetry. This is chiral. How about that one?
Achiral.
Achiral, why?
Because there's no chiral carbons.
No chiral carbons? How many planes of symmetry does that compound have?
2.
Compound's got 2 planes of symmetry. That's 1. And the other one is where?
Right through them there.
Two planes of symmetry. Over here.
Achiral.
Well, it's gonna be
It's got a place of
chiral.
symmetry.
Is it meso? Meso.
Methyl coming forward, mirroring the methyl coming forward. Half a bromine back, mirroring half a bromine back.
So meso.
Plane of symmetry. Two chiral carbons. We could get into some vague answers if we go deep enough. Is that carbon chiral?
No.
No.
Bromine H, you get the same going both ways. That one's not. Two chiral carbons. Meso, because it's not chiral as a whole. This is another way. You might see rings like this. This is a 5-membered ring, but instead of it drawn flat on the board, okay, it's drawn as if it's like this. So this part that's down is now forward. And since it's forward, it's sort of drawn bolded that it's coming forward. So that's another way to possibly see rings. And it's actually better to take these back to flat on the board until you get good and you just kind of see it. But I would recommend taking these back to flat on the board, maybe redrawing them, same way. See how you can deal with those, and we'll look at those tomorrow. Then we'll be moving down to these reactions. We'll go back to our alkene reactions, and we'll look at the stereochemistry a good bit. There's also alkene reactions in that handout that we sort of skipped. I asked you to do them wrong. We'll go back and look at those. Please bring your questions.